Um, so we can move to the last question, last speaker of the session. So welcome, Alex. So Alex McCaskey is a senior quantum computer and software architect at NVIDIA. Alex, whenever you're ready, you can start with your talk. Thank you.
Great, and you can see everything here?
We can see everything.
Oh, great. Okay, perfect. Well, yeah, thank you so much for this opportunity to be here. The previous talks have been really interesting, so I'm excited to be here, and I'm excited to present today on what NVIDIA is doing in the quantum computing space, specifically thinking about accelerating quantum algorithm research with a new product called cuQuantum. So NVIDIA obviously is very famous for its CUDA platform, its CUDA programming model, and building libraries on top of this. For different mathematical tasks, different application, use cases, QFTT or QFFT, QBLAS, and all these different things. And now we've got a new circuit simulation tool called cuQuantum, and I'll be kind of focusing on that for this talk. What I'd like to really get across is what is our motivation? How do we see kind of our quantum computing roadmap, and how does it fit with the broader quantum computing ecosystem that is out there today? So what is the need really here for classical HPC, classical heterogeneous computing with GPUs in regard to circuit simulation? And then we'll dive into the specifics of what is cuQuantum. So I'll talk about the two main components of cuQuantum, QStateVec and QTensorNet. How do we see it in this broader ecosystem? How do we use it? What kind of speedups are we seeing? And we're seeing really good speedups so far. And we're in very early days here with cuQuantum, but we're seeing good speedups. I'll talk about some of the latest QAOA MaxCut results that we have that are really interesting and scaling us to a very large number of qubits with tensor network methods. And then I'd like to end up with a focus on how do you program something like the cuQuantum backend simulation capability, or really any backend, any physical backend, IBM, Honeywell, Rigetti, what have you. In an HPC context. So specifically looking at a product that I put forward in the past for programming quantum computers in C++ called QCOR. Okay, so let's get started. I want to start off, just kind of lay the motivation down for where NVIDIA fits into this broader quantum computing space. We sat down and thought about what is our current research roadmap for quantum computing, and we decomposed, like many do, what are the expectations for quantum computing in the near term, the far term, what has happened in the past, this type of thing. And we decompose it into these three different phases, right? So we're kind of coming out of this quantum supremacy realm, whereby we've seen, certain experiments that demonstrate, some well-defined problem on a quantum computer versus a classical computer. And we see some signature of a speed up, right? So specifically, I'm thinking about the Google supremacy example. And what can we do with these near-term architectures to really kind of understand application benchmarking and programming models and algorithm research and things like this. It's a very important time, and active research for us here is can some of these things be efficiently simulated on GPU supercomputers? And we think yes, and we think moving toward this kind of broader NISQ era, pushing past this supremacy threshold and thinking more broadly about noisy architectures with many qubits, and can we have some impact there as well with HPC, with classical HPC, and understanding, how can we really demonstrate strong quantum advantage for certain workloads. And then, of course, looking to the future, we obviously, envision the fault-tolerant quantum computing era, millions, tens of thousands, hundreds of thousands, millions of qubits, physical qubits mapped down to logical qubits via standard error-correcting codes, and what kind of classical HPC GPU technologies may be necessary in that realm as well. Thinking about error correction, decoding algorithms, and things like this. And of course, all along the way, thinking about in the near term, in the NISQ era, variational algorithms, and how can we enhance quantum classical workloads. You may think of classical applications that leverage a large number of GPUs, but maybe offload some certain small quantum subroutine to an available QPU. Where can we play there? And so we think that GPUs and heterogeneous computing is obviously going to be important as we move forward here. And this is our QC research roadmap. So speaking specifically about the near term and circuit simulation, so we're very interested in how can we push the envelope with regards to quantum circuit simulation. There's been a number of groups out there that have obviously leveraged GPUs for this, but there's not really been kind of a robust solution that can be dropped in to a number of different simulation backends and leverage these massively parallel distributed multi-GPU architectures. So how can we integrate and take advantage of classical HPC to accelerate hybrid quantum classical workflows? And the real questions that are driving what we're trying to do here, what quantum algorithms are promising in the near term and long term for quantum advantage? What are the requirements for quantum advantage? And what quantum processor architectures are best suited to realize these valuable quantum applications? And we think that we have a role to play here in that we've deployed these multi-GPU architectures. We're using them across a number of different fields, from machine learning to scientific computing and what have you. And we think that our expertise can be leveraged here for circuit simulation. So, here's kind of a simplified view of where we're going with this for specific quantum circuit simulation techniques. This is not obviously, a comprehensive list of how you can simulate quantum circuits, but there are two that we've picked up on that have become fairly ubiquitous in the research community: state vector simulation and tensor network-based simulation. And QQuantum is really focused on both of these approaches. So on the left side here, we have state vector simulation, which most approaches leverage this this concept, right? You maintain the full 2 to the n scaling qubit vector state in memory. You're updating the state at each circuit time step via some unitary matrix application. Obviously, the drawbacks here are that the memory capacity is limited, right? And that this grows exponentially with the number of qubits. And you can only really push toward, the 30, 40, maybe 45 qubit range with a supercomputer. However, on the other side, we have the tensor network methods. And the tensor network methods are interesting in that they give us a method to tune the memory usage, essentially, right? So we can start to think about simulating, to some approximate sense, hundreds or even thousands of qubits for certain practical quantum applications. And the really cool thing about both of these is that GPUs are a great fit. So on the state vector side, there's really not much CPU to GPU memory movement. You can kind of initialize the state vector on the GPU memory RAM at initialization, and then just do operations entirely on the GPU in parallel. And then on the tensor network side, we have our GPU tensor cores that are really good at these MATVEC accumulate type operations, which are critical to tensor network contractions, right? And so there are a number of approaches here that really map down well to GPUs. Okay, so let's introduce QQuantum now. QQuantum is an SDK of optimized libraries and tools for accelerating quantum computing workflows. So just to kind of get this part out of the way, what is QQuantum not, right? So it's not a quantum computer. It's not a quantum computing framework like you'd see with Qiskit or Cirq, or even what I'll show later, XACC and QCOR. And it's not even really a quantum circuit simulator per se, right? So things like Qiskit Air, XACC's TNQVM, QSIM from Google, some of these other like simulators that you can download and run with. QQuantum sits at a layer lower than that. Okay, so QQuantum is an SDK. It is a public API for that provides certain functions to do typical, on the state vec side, typical MATVEC type operations and typical measurement of the qubit state, the qubit register state operations, right? So sampling, computing expectation values, things like this. On the tensor network side, it's an API, a public API for things like tensor network contraction path optimization, or creating tensor network graphical structures kind of in memory on the GPU. So it sits at a low level of abstraction, and it's meant to be a backend for these other types of quantum computing software products to delegate to. right? So quantum circuit simulators that are already targeting NVIDIA GPU architectures can now, instead of handwriting GPU kernels, can now target something like cuQuantum. Same thing with Qiskit Air. And these are two of our partners that actually have picked up on cuQuantum and are showing and demonstrating scalability and speed up results that are really interesting. And then, of course, the quantum computing frameworks, they delegate down to the circuit simulators, which ultimately delegate down to the quantum SDK. So it is a platform for quantum computing research, right? This foundational layer that provides an API for interacting with our GPU architectures, specifically for circuit simulation tasks. And because it sits at such a low level, this MATVEC application level for QStateVec, for instance, you can simulate ideal qubits, you can simulate noisy qubits. It's really up to the application. It provides a large level of flexibility with regards to what you can use it for because it sits at this foundational layer. And so the idea here is to enable algorithms research that scale and performance not possible currently on quantum hardware today, or even simulators that are available today, to kind of push that envelope, right? And so right now, if you'd like to try this out, QStateVec is publicly available. A public beta is out now. You can go download it. You can build against it and use it. It's integrated with Circ. It's going to be out with Qiskit this month. And Penny Lane, which is another kind of machine learning framework, it's coming out for that in January. So we're pretty excited about that. So let's get started with kind of the details here. So we'll start with QStateVec, state vector simulation with cuQuantum. The APIs are specifically designed for state vector simulation and operating in place on the GPU to save memory usage and memory transfers, okay? And our preliminary benchmarks are showing like a 20 times improvement over CPU implementations with just a single, NVIDIA A100 GPU, for instance. And to give you an idea of kind of what I'm talking about at this low level, right? I mean, here's a function example from the API itself, right? You'll see this in qstatevec.h in the header file. We basically provide this low level of user control where you specify the unitary matrix representing the gate that you want to apply to your simulated quantum circuit, right? And the memory is handled internally on the GPU, and there's no real need for you to have to do any of these kind of complicated and taxing memory transfers. And so common use cases here, measurement on a z-product basis, single qubit measurement, applying gate matrices, all sorts of things are here for typical simulation tasks for state vector simulation. On a single GPU, here are some early results. On the left here, you're seeing a A100 GPU with 80 gigabytes of RAM versus a 64-core multi-threaded CPU. This is all built within Circ's QSIM simulator, where we're demonstrating this. And you see for typical algorithms, Fourier transform, Shor's algorithm, and even the supremacy circuit at a depth of 14, we're seeing pretty good speed ups as we increase the number of qubits over the CPU only approach. All the way up to almost 20 times speed up for Shor's at 30 qubits, 14 times speed up for the Sycamore circuit at 32 qubits. And then also, we can leverage this for variational tasks as well. So the VQE speedups that we're seeing here for kind of typical chemistry example for different molecules in different basis sets here. For this final one, C2H4 on 22 qubits, we're seeing a speed up of close to 20 times. So this is really good results. Moving this to more of a multi-GPU approach is kind of where we're headed. The big product offering from NVIDIA, or one of them on the hardware side, is this DGX A100, right? The DGX A100 comes with 4 A100 GPUs, each having 80 gigabytes of RAM. And so we're designing the underlying APIs, the underlying implementation to take advantage of however many GPUs are available on the hardware, right? And so here for QStateVec, I mean, we're seeing basically strong scaling here as we increase the number of GPUs available. And then building this out to larger systems like our internal supercomputer Selene, which is a bunch of different DGX A100 superpods essentially connected together. And so what we're doing is in early Q1 of next year, we'll be releasing what we call the DGX Quantum Appliance, which essentially is a container. This had a timer on it, sorry. Which essentially is a container which has Circ with cuQuantum support built in. It's kind of a holistic workflow. You know, you can kind of start at the application level and target something like the DGX A100 from a containerized approach, and this will be coming out in the next couple months. All right, switching over to QTensorNet. QTensorNet is a library to accelerate tensor network-based quantum circuit simulation. To give you an example of some of the tasks that are really important here, if you look at this figure, you know, not all tensor contraction path sequences are the same, right? So it's really important to have libraries that enable one to input some tensor network and output the optimal contraction path, right? So that we can leverage or use the correct, you know, the optimal sequence in the computation itself, right? So QTensorNet initially will provide this type of functionality. It'll provide an API for calculating optimal contraction paths, subject to memory constraints and parallelization needs. You know, hyper optimization is used to find contraction paths with the lowest total cost, where the metric here is like flops or the time it takes to compute this. You know, under the hood, QTensorNet is actually leveraging the QTensor library, which is another one of the math libraries coming out of NVIDIA. And it leverages QTensor for specific heuristics to calculate these types of optimization or optimized contraction paths, and then ultimately for execution itself, right? So multi-GPU execution of that specific contraction workflow is offloaded to QTensor under the hood. And you're presented with kind of a high-level, you know, API where you can construct tensor networks for your specific circuit simulation task and compute optimal sequences for contraction paths and then offload it to whatever multi-GPU architecture you have. And of course, this is really interesting for a whole bunch of different tensor network approaches, right? You might have the kind of naive contraction approach, but you might also decompose your quantum circuit into, you know, different wave function decomposition structures like, you know, tensor trains or PEPs or Mira or tree. You know, this API is meant to provide these types of abstractions. And so what kind of speedups are we seeing here? Here on this bar graph, lower is better. And we're comparing QTensorNet's optimization cost calculation with others in the field. So the kind of one of the big ones is Catangra, which I believe is coming out of the Caltech QUIM work, but I may be wrong there. But and then of course OptEinsum, which is coming, which is a popular Python package. And you can see that QTensorNet is basically keeping up with Catangra and is definitely improvement over the Python approaches in computing these optimal contraction paths. And then on a single GPU, here are some results, some scalability or some performance results for different algorithms using the QTensorNet contraction path calculation mechanism versus just standard QPy, just kind of using the tooling and the available kind of programming model from QPy. And we're seeing, you know, pretty good speedups here, right? We're seeing for the deep neural network approach on 16 qubits, we're seeing close to, you know, almost 20 times speedup. And then, of course, in the 10x speedup for some of these other algorithms. Okay, so let's focus on a recent result that's leveraged the tensor network work, the QTensorNet backend in QQuantum. Specifically targeting the MaxCut problem. And this has become a really popular algorithm in the quantum computing world. You know, recently it was discovered that the QAOA is a good fit for solving this problem. MaxCut is an NP-complete combinatorial optimization problem where you try to find the cut across edges of a given graph that maximizes the edge weights in each cut, essentially, right? And so there's applications to this in clustering and network design and statistical physics, etc. You know, it's an early target for these hybrid variational algorithms, specifically the QAOA. And there's been several hardware demonstrations, and you know, here we highlight that they've done this on the Rigetti 19-qubit chip, and this was done a few years back. Okay, so taking this and simulating it with tensor networks, this has been shown in the literature over the last few years, culminating in this 2020 paper from colleagues at Argonne National Lab. I believe they showed low 200 number of qubits or nodes in the MaxCut graph for a QAOA-based simulation on the Theta supercomputer, I believe. Anyway, this summer, we have colleagues here at NVIDIA Research that have put forward a new algorithm for simulating MaxCut on something like QTensorNet. And what they've done is really interesting. They've basically mapped the MaxCut problem from a standard Ising model to an Ising model with this XIXJ term. And instead of doing it on n nodes or n qubits, they've halved the number of qubits. So and in doing so, they've built up a loss function that allows them to extract information about the original problem out after some variational approach. And so basically what they're doing is they're mapping this MaxCut graph onto a 1D tensor ring in a multi-basis encoding. And so instead of simulating the full number of qubits, you're simulating half of those number of qubits. And they were able to do this with tensor network methods on 512 vertices for the MaxCut problem, which was a 256 qubit simulation on a single A100 GPU. And if anybody's more interested in the work, here's the archive paper, and there's some code associated with it on GitHub to go check out. We took this and scaled it to something like Selene. So using QTensorNet and the multi-GPU architecture provided by the Selene supercomputer, we were able to take that original result. The Argonne result was at 210. The original result from our NVIDIA colleagues was 512. And we were able to scale this to 1,688 qubits, a 3,375 vertex MaxCut problem. And since this is a variational approach, we were able to get it within some accuracy, right? So we got this to within 97% accuracy. And then, of course, we also pushed this even further on the same architecture for a 5,000 qubit problem. And these are using the tensor network methods provided by QTensorNet. Okay, so to wrap up here, I'd like to kind of show you where we're moving toward with regards to how would I program cuQuantum or any other physical quantum architecture in an HPC context in something like C++, which is a very familiar, very popular language in the HPC world. So here I'd like to introduce a new compiler that's recently been put out. It's completely open source. It's a C++ compiler for quantum classical computing. It's something that I've been involved with for the last 2 or 3 years. It's an extension of C++ that provides quantum programming via the definition of standard functions annotated with a QPU attribute. So we have quantum kernels that can be then compiled by the compiler to any available physical or simulation backends. Okay, and so just to give you an example, here's a very standard phase estimation algorithm, right? This is the circuit you would see on the Wikipedia entry, for instance, of the textbook phase estimation algorithm. We start off, we put this first register in a uniform superposition with Hadamard's. We put our eigenstate register into the eigenstate. So whatever we do whatever state prep is necessary to generate that state. We have our controlled U rotations here. We have our inverse quantum Fourier transform. We have our measurement application, right? So this is pretty easy to read, and it's pretty easy to write this in the language extension provided by QCOR, right? So here we have our typical C++ main function. QCOR elevates or promotes the use of a new data type, a QReg, a register of quantum bits, and it provides an allocator for these quantum bits. So we can say QAlloc in kind of a similar way that you would say malloc in the classical world, or alloc. So we can allocate, a number of qubits, and then we can call kernels that have been defined in the language, right? So here I have a phase estimation function, QPE. It takes a register, and it takes a general kind of oracle function, the unitary that we'd like to apply as part of this phase estimation algorithm. It's annotated with this QPU attribute to note that it's meant to be compiled and executed on the attached quantum accelerator, be it physical or simulation. And then the rest of the code really just kind of follows what you see here in the picture, right? So we put the bottom register in whatever eigenstate we want to put it in. We apply Hadamard's across the top register here to create a uniform superposition, and then we can use standard C++ control flow for loops, for instance, to loop over and apply these controlled unitaries. We can pull in provided standard libraries for very common algorithms like this IQFT call, and then we can perform measurement. And then, of course, all this is a standard C++ file. We have a compiler for it. We can compile it to a.out. We can specify the QPU we'd like to target. Here, I'm specifically saying I'd like to run this on QStateVec with a certain number of shots, and I can execute that just by executing the produced binary. So this is a really interesting way to integrate HPC resources with quantum acceleration, in my view. And it's a very familiar approach in that it promotes a standard language extension and a standard kind of compiler workflow. The way this works is QCOR builds off of Clang and the XACC framework to take these kernel representations and lower them down to something in the XACC-IR, the intermediate representation for XACC, and then ultimately to hook up any available backends that XACC supports for execution, which is IBM, Honeywell, Rigetti, the QStateVec, QTensor network, TNQVM, some of these other simulators as well. Moreover, and I'll show this here in a sec, QCOR is now providing tight integration with the new QIR Alliance, this quantum intermediate representation that's building off of the LLVM infrastructure. QCOR supports this fully pretty much and enables one of the only open source OpenQASM3 compilers, all through the QCOR compiler, and I'll show that here in a sec. I wanted to show what it would look like in QCOR to target something like QStateVec for a variational algorithm. And it's pretty straightforward, right? So here, take the typical VQE, which we've heard about earlier. You have some state prep ansatz. You have some observable, some operator that you want to compute the minimal,
Alex, you have a minute left.
Oh, okay. Thank you. Thank you for telling me that. I have one more slide. I'm done pretty much in a sec. So anyway, here's how you would do a variational algorithm. It's fairly straightforward. We have an entire data API for different variational tasks, and the compile step looks the same as before. And you can target whatever backend that you're interested in. And then finally, like I said, we're building off of the MLIR infrastructure and targeting the LLVM QIR infrastructure to enable things like OpenQASM3 compilation down to hybrid quantum classical executables that target whatever QPU backend that you desire and specify at the command line. And so this in and of itself is a whole talk in and of itself. So I'm not going to go too much into it now that I'm out of time. But yeah, this is an interesting approach to quantum classical programming and compilation in a hardware agnostic fashion. Anyway, so this is what I wanted to present, QQuantum and programming QQuantum and how we can use this to accelerate algorithms research. And I hope that I've got that across today. And with that, I'll end. And if there's any questions, I'd be happy to answer them.
Thank you very much, Alex, for your excellent talk. So if we have any question.
Yes, please. Thank you so much, first of all, for having accepted the invitation to talk and for the great talk you gave. I have a question. I missed if your libraries can manage only gate model quantum computers or also, for instance, a measurement based.
Yeah, that's a good question. So at this point, it is basically only gate model quantum computation. We do not do provide any API for the measurement-based quantum computation. But this is a growing project. This is kind of early days, and we're obviously interested in feedback. So these are things that we'd like to kind of work with people on and collaborate on, and perhaps this is something that can get baked into it in the future.
Thank you.
Okay, thank you very much, Alex. So this was the end of the session. It has been an amazing session, so I would like to thank all of you and all the speakers for their excellent talk. So I leave the floor to Davide Ottaviali for the concluding remarks. Thank you.